So I'm now going to hand over to Iain, who you remember from this morning. He and some of the other people from the evidence team have been spending their lunch break looking through all of the questions that you've been asking. And there were lots and lots of the questions that you've been asking. So that's what they've spent their lunch break doing. So we're going to hand over to Iain now to start answering some of them for you.
Yeah, so that was my lunchtime, was wolfing down some pizza and looking through a whole bunch of questions. It's 7 pages of questions you've got, which is fantastic. I've just a couple of things before I kind of start, really. I mean, one thing is many of the questions that came up really are not necessarily relating to the session that I did on the science, but are absolutely legitimate questions about, sometimes the process, sometimes about aspects like, what is the power and effectiveness of Scotland and the climate change area, which are things that we'll talk about particularly later on in today's session. Also things about like what is net zero, or things about specific emissions, sources of emissions or impacts of emissions. And just to flag that tomorrow in particular, well, we'll start it today and then roll into it tomorrow, we will be talking about things that do, where are the emissions coming from globally, and then more specifically for Scotland, and then also what we do about it. And then just a reminder of something that was mentioned earlier, next weekend, weekend 2, we'll really look at Scotland. So some of the questions that relate specifically to those I'll probably park, because literally I think I haven't added it up, but it's probably 100, 120 questions there. So that's the other thing. I think the other thing to say is, I dealt with climate change or climate science in 10 minutes. People do PhDs, master's courses, etc. You're not here. In fact, the whole 6 months is not here to do a kind of online course about climate change. But I think it is important, and that's why we put it up front, to talk about some of the science. But it's complicated, and so what I've done really is flag a few of the general points, particularly points that came across from multiple groups. And I thought I'd just chat through them, really. I mean, normally you have to have a health warning when I say, I'm not a climate scientist, but that's not a cop-out clause, because I have done programs on climate science. But we will have, and particularly you'll meet some of them tomorrow, who are climate scientists. That's what their job is. And I think the other point that's worthwhile emphasizing here is there are further kind of supplementary information videos, particularly, that we either have got or could have out there for people who really want to drill into this in more detail, because it's, in one level, it's very complicated, but in the other level, some of the basic aspects are relatively easy to get across. So I thought, rather than show you graphs and tables and all the rest of it, then what I would do is just chat through them. Now, there are other people from the evidence group, I think maybe Kate's on, that might want to chip in, and if they do, all I'd say to them is just unmute and just jump in if there's a point that you'd like to make. But I thought we'd start with one. There was a number of questions around consensus, the idea that the science is settled. So we've taken the approach here that we haven't, as you might have expected, have a whole session about whether climate change is real or not. The starting position for the Assembly and for our evidence base has been it is happening. And there's 2 reasons for that. One is that this has come off the back of the Scottish Climate Change Act. So there's legislation there which says climate change is happening. What are we going to do about it? So we're not unpicking that. That's our starting point. But probably the more important one for me as a scientist is this notion that for the scientists, the science is broadly settled around that climate change is happening, that humans are a major part, a dominant part of that issue. And that is something that we clearly, in the broader kind of public, etc., is still something that's talked about. So I'm not, there'll be many people within the Assembly that have still got big question marks about that, and that's absolutely fine. So I thought that so one question was, about the scientific consensus and how it's evolved, changed over past decades. So I thought I'd maybe say a little bit about that, because in many respects, the signs I put in my little film that, you know, in 1965 we have a president of the United States talking, essentially saying in the basis of the science that the burning of fossil fuels is changing the chemistry of the atmosphere and producing warming. So, you know, we knew by the 1950s that science was so well established that you know, a major leader of was actually saying that. And yet that doesn't feel like what it is today, does it? I mean, it still feels like there's lots and lots of arguments around that. And I think that, you know, in the early years, there really wasn't any significant discussion about whether the science was right or not. The science was broadly accepted. I think my view, I think around about 1980, it switches when Ronald Reagan comes in as president of the United States. And alongside the science, there's brought on board economists about whether this might be a good thing or a bad thing for the economy. And suddenly the idea of the global warming, as it was referred to then, suddenly kind of leaves science and becomes a wider topic of debate in political circles, because it's, you know, what do we do about it? Brings in tax and economy, etc., and suddenly becomes a much more contested issue. But essentially, throughout that whole time, from 1940s, 1950s, 1960s, the actual science of the climate maintained itself as being something that was broadly agreed. So the first climate models started to be built in the 1970s, and although there were different models, they all started saying the same thing, which was that we should expect warming, we should expect it to be bigger in the Arctic, we should expect sea ice to change, a whole bunch of different things that you'll hear more about. But taking us up to the present day, I think the point that I would make is that when a scientist says about they're talking about climate change, they're doing so with a constituency. So every major national scientific academy on the planet and almost every scientific organization has a statement that accepts the reality of climate change and the reality that human influence has got something to do with that. And in terms of those kind of statements, that actually includes almost all the major oil companies as well, oil and gas companies. So even those that are involved in fossil fuels necessarily are not contesting the science. Maybe they might be contesting what we do about it, but a very small exception of particularly in some of those industries would contest that. But the science group is completely solid on this. You'll probably hear something about 97% of scientists say, and this is a phrase, and well, there's a video that we can link into in resources about this, which is that there's been various studies of all of the literature, all of the academic studies that have been done around climate change, and to what extent the scientists have said they're for it, you know, they accept it or they don't accept it. 97% of those academic papers showed that the science was saying this was happening. And our more recent studies, even that 3% turns out to be not saying it's not happening. So it's a hard one to think about, but the absolute vast majority of those people who study the climate are saying this is happening. And that was something that really surprised me when I made that Climate Wars film, was realizing that the debate was happening at the fringes of the science. The main people who study this, this is their expertise, were absolutely unequivocal about this. So there is disagreement among scientists, and you might encounter it over the coming months, really, about scientists talking about this. But they look at that carefully, because their arguments are really about what we're going to do about it. Or it's maybe about nuances about how important one change would be versus another change. But it's not about whether it's happening or not. So there's another question about what do we say about skeptics and things like that. Of course, there are people out there, but often the arguments when you hear about climate science is very quickly about what we do about it and the economics of it, etc. The actual physics of it isn't what's contested. So that's the reason I say our starting point is very much around consensus, that we're starting from. Our starting point is it's happening now. What are we going to do about it? Another set of questions really came around about 1 degree, 1 degree rise by the end of the century. Surely that's not very much, it seems like hardly anything. Why are we talking about this as an emergency? Someone's got 1 degree since 1880. What does that actually mean? So I guess a couple of things there. There have been changes. You know, we've been recording temperatures. Well, in the UK's got the longest temperature record there is, but we've been measuring it and measuring it with ever more coverage and ever more accuracy, and as we've gone through. But that temperature hasn't been absolutely rising constantly. So there are times when there's fluctuations. There's times when there's less temperature rise, or indeed when there's been cooling. So a good example of the cooling is around about the 1950s. There's a period of cooling around the world, but certainly we get it in the UK. And so what's that all about? Well, ironically, one of the things that we think happened in the 1950s, those people, so maybe people on the call that remember us, is that post-industrial, certainly Europe, Britain, there was the smog, was the huge pollution that was affecting there. And so when the Clean Air Act comes in and cleans it up, what we really see is there was a background warming all the way through that. It's just that the aerosols, that thick atmosphere that happened in our smoggy cities, was actually not allowing the heat to get in as much, and we was producing a net cooling. And then there's other things when volcanoes come in and produce ash that cover the planet, and that again produces some cooling effects. But broadly, and those are these kind of fluctuations that happen. We see there was a graph, an animated graph in the video that shows these things bouncing around. So our temperature is not a then steady increase, but it has been, and certainly in the last 30, 40 years, an accelerated steady increase. But going back to this notion of 1 degree, I think the key thing for me, the way that I think about it, is it's the core temperature on the planet, not the actual physical inner core of the planet. But if you think about our bodies, we can deal with loads of different temperature change. You know, we walk outside, we put something on, it's cold. Our bodies know it's cold, and then we might go somewhere really warm, but our bodies know it's warm, and we can tolerate that. But what our bodies what can't be tolerated is our core temperature changing really dramatic. If our core temperature, and anyone who's having 2 kids with babies, things like fever, if a very small temperature change for the core temperature of human bodies make a really big difference. And that's the way I think we need to think about it in terms of the climate, which is that there's this fundamental temperature for our planet, which everything is kind of attuned to. Our climate's attuned to, often, but the biology is attuned to it. So different organisms, for example, will go through, based on seasonal changes, very, very subtle changes in temperature will trigger biological changes that happen. So our planet, our world, our natural world, is very well tuned to the temperature that it's evolved into over the past millennia, tens of thousands of years, etc. And that it's that aspect changing that is causing the effects. So a temperature difference of 1 or 2 degrees that we'll be talking about, as I say, it tends to be thought of as, well, surely we can just adjust to that. But the point is the dynamic changes of the planet's processes will change. So you hear about the loss of sea ice, for example, which is very temperature dependent. Loss of glaciers, for example, very, very temperature dependent. Changes in the oceans, where some of the biological effects in the oceans are very tuned to particular temperatures, like organisms making their shells out of calcium carbonate, for example. Tiny changes can put whole ecosystems or whole natural systems over the line. And it's worthwhile bearing in mind that, you saw a jagged graph. At one point it goes jagged, that's the ice ages coming and going. And then we suddenly get this graph that goes right up. That's the CO2 record. But the point is that this planet, our planet, is so finely tuned that it goes in and out of an ice age, where we get the growth of ice sheets in the north and the south. It's about 3 degrees Celsius temperature range that kicks that in and out of. So even, as I say, the planet's so finely tuned that those essentially small changes to us actually have really big effects. So we might not be able to feel 1 degree temperature change in terms of our sensitivities, but often, as I say, we see it in other things. So often farmers can see it necessarily in their baselines, bird watchers often see it. Anyone who's kind of connected to the natural world can often see the effects of that. And a few people in the comments made things about changes in the weather that they're, kind of consistent with, and that kind of fits that. Another question, or set of things about the sun. How much effect does the sun have? That's important because the sun is the driver of climate. So if we look at it, the changes in the Earth's orbit relation determine the amount of sunshine that we get, and how it's spread across the planet. And that is the fundamental driver that has existed for millions of years about our climate. And so the sun's variations continue to have an effect. The difference is really that the big effect that we've seen in the last century, that we cannot explain that by the sun. We could in the first few decades of the 20th century. That does seem to match it. But then really from the 1950s onwards, you'll see a graph, the solar variations goes one way and we go in a different direction. And that's that anthropogenic, that human influence. So there is still solar variation there. The sun is having an effect, but it's very, very small. The dominant effect you cannot explain by the sun. And we now have satellites up there that are looking exactly for that reason at the sun. So our data on the sun is better than it's ever been. And we know that we can't use the sun as an excuse for this. Yeah, what else we got? So I mentioned modeling in that presentation, and this tends to be something that people pick up quite often on about how accurate is this modeling, how much variation is it? And there is this thing that, well, these idea of models, computer models, are like playthings that we can just kind of mess around with and tweak it to make it fit with whatever we want. But that's a fallacy, really. And the reason why it's a fallacy is because these climate models are based on well-founded physical principles of how the Earth works. And that physics was worked out mid-1800s, 1859, I think it was. The Irish scientist John Tyndall was looking at the physical properties of the air and infrared radiation, and realized that atmospheric CO2 created these barriers that radiation that was getting bounced back off the Earth wouldn't actually make it through the atmosphere. And so that 1859, he discovered the greenhouse effect. So this has been known for some time. So the models that run on basic physics, and in fact, I think I mentioned it in the presentation. The Met Office, the UK Met Office, that does all the data for weather forecasting, is essentially that runs on the same supercomputer model that they run the climate models on, the future climate models. It's a stripped down version. It's not as complicated, but it's essentially the same thing. So the difference is that rather than trying to say, is west of Scotland going to get more rainfall in 100 years, it's kind of saying, is it going to be wetter? Is it going to be hotter, etc.? It's not get the same kind of precision going into the future, but it's the same physics. And what that allows us to do also with the climate models, to test it, what you can do is you can run the model backwards. You can say, right, this is how we think it works. Now let's work it back and go back a few centuries, and we can compare it to changes that's known happened in the past. And so this way of kind of calibrating the models by looking backwards is an important way. But I think the main thing probably to emphasize with the modeling, the climate models, is there's a whole ton of groups around the world who are working on different models, slightly different values in them, etc. And that might think, oh, that's crazy. Why have they not got the same model? Well, it's for precisely the question about the accuracy of these models. They're all got the basic physics in, but they're taking decisions about slightly different parameters, slightly different values, and then they run them. And then they run them hundreds of times with slight changes. So any model, any single model or any single simulation is unreliable. It's the population of the simulations, the population of the models, that is the important thing. If all the models tell you the same thing, regardless of their individual idiosyncrasies, then you can be pretty sure that is going to happen. If some of the models show one thing and most of the models show something else, that's an important characteristic, and you should look at that. So what, as I say, what we talk about then, when we talk about climate models, is this suite of models. As I say, we've got different groups, even in the UK, running different types of models, and they all get together. And there's a whole big part of the kind of climate science is about how accurate are these models, constantly getting tweaked, constantly getting modified. So for that, it feels like a little bit black box to the rest of us. I'm not a model, I don't understand them, but it is important to realize that we can't just change them for our own sake to make things warmer or hotter or whatever it is. They are based on this basic science.
Great. Iain, fab, you have 1 more minute. Is there anything you'd like to say just to wrap up?
Yeah, just that there's lots of stuff about things like methane and the IPCC. We're really going to be looking at many of these aspects again. We'll follow up on tomorrow. So this is really a long learning curve for us over the next few weeks and months, really. And the key thing there is that it is complicated, but actually, do you know what? The more complicated bit is what we're going to do about it. And that's what the Assembly members are all here for. So thanks for that.
Fantastic. Thank you so much, Iain, for giving responses to many of the questions that you posed earlier today. I'm sure lots more questions are going to come up, both from what you've heard there, but also as we move through the process. So we're going to give you as much time as possible to digest what you hear, but also to have discussions and also to have other opportunities to ask questions. So thank you all for listening to that and to listening so intently. Just a reminder, I mean, as we go through, we are of course going to be hearing quite a lot of information. I'm aware that in your introduction and in your packs, it was suggested that you find a way to take some notes for yourselves as these talks do happen. So please do continue to take notes in a way that works for you. I know some people like to write, some people even like to draw, some people like to sit back and listen and absorb, but please do what works for you. And if you have any questions or any support needs, please let us know and we'll help you out. So once again, thank you very much to Iain for doing what I'm sure was not an easy task, but I'm sure it's given us lots of food for thought. So we're going to take a little bit of a break from that conversation for now to turn our attention just to something else. In this next section of the session today, we're actually going to be hearing a different type of presentation, which isn't about climate change, but is instead about how you as members of this assembly might want to approach the information you are hearing during the presentations. And I did note from some of the questions that you generated this morning, there were quite a few questions in there actually around kind of evidence and data and things like that. So what you're going to hear now is really related to the information you're going to be hearing during the presentations and how you might want to approach that. So to kick us off, we actually have a video from someone called Anna Renwick from the University College London, who has been involved in quite a few citizens' assemblies in the past. And what's happened is he has prepared this short video for you that asks you to think about how you think about the information that you're hearing, and also to consider how you can use that information to build up your own knowledge and understanding of the topic of climate change, as well as to also inform your discussions going forward. So we're going to play you a video just now, so feel free to kick back and watch this video. And shortly after the video, we'll be going into breakout groups just to have a chat and digest what we've heard.